Here's how a lot of people start their first machine learned potential project. They install Mace, point it at their system, and immediately start training a model from scratch. 2 weeks and several thousand DFT calculations later, they finally have a working potential, one that a pre-trained model could have handed them on day one, for free. So before you train anything, the first question isn't how to train. It's whether you need to at all. There are 3 ways to get a machine-learned potential, and they cost wildly different amounts of effort. At the bottom of the ladder, take a foundation model off the shelf and use it exactly as it comes. No training, just minutes. In the middle, fine-tune that foundation model on a small dataset of your own, some training, maybe a few hundred reference calculations. And at the top, train a model completely from scratch. Thousands of calculations, a carefully built dataset, and by far the most work. The classic mistake is starting at the top. The smart move is to start at the bottom, and only climb when your system actually forces you to. So what's sitting at the bottom of that ladder? A foundation model, something like Mace MP, is a single potential that's already been trained on over 1 million structures, spanning almost the entire periodic table. 89 elements, 1 model. You hand it atoms, it returns energies and forces, with 0 training on your part. For a huge range of ordinary inorganic materials, it simply works out of the box. Which means the very first thing you should do, before writing a single line of training code, is just test it. Testing it takes 3 quick checks. First, accuracy. Run a handful of your structures through both the foundation model and DFT, and plot one against the other. If the points fall on the diagonal, the model agrees with DFT. Second, stability. Run a short molecular dynamics simulation and watch the total energy. If it stays flat and well-behaved, your potential is holding together. Third, a physical property you already know, a lattice parameter, an equation of state. And check that it lands where it should. For a clean, standard material like this perovskite, a foundation model will often pass all 3 on the very first try. And if it does, you're finished. Stop right there. Don't train anything. But now point that same model at a system it has never really seen, unusual chemistry, a rare oxidation state, something far from ordinary bulk crystals. Watch what happens. On the parity plot, the points pull away from the diagonal. Systematic errors, not random scatter. And that molecular dynamics run. The energy doesn't stay flat. It drifts, then climbs, then shoots off the chart as the atoms fly apart. That's the model extrapolating into territory it was never trained on. And this failure is actually the most useful result you can get. It's the model telling you, precisely, when it's time to climb the ladder. So here's the whole decision, mapped straight onto what you just saw. If the foundation model is accurate and stable on your system, use it as is, and you're done at the bottom rung. If it's close, the right shape, but with a steady offset or errors that are just a bit too large, then you fine-tune. You're nudging a model that already mostly understands your chemistry, and that takes only a small fraction of the data. And if it's badly wrong, exotic bonding, charged systems, or an accuracy that foundation models simply can't reach, then, and only then, you train from scratch. The rule is simple, let the size of the failure decide the size of the job. Not habit. So before your next potential project, earn your way up that ladder. Test the foundation model first. Let it pass, or let it fail, and let that result tell you which path you're truly on. Because the most expensive mistake in this whole field is training a model you never needed. In the next video, we take the hardest path, training from scratch. And tackle the question every tutorial quietly skips: where does your training data actually come from?